So in this example, we're going to use all the rules that we've learned so far in order to calculate the view factors f12 and f21 in the three different shapes. Of course, some of these shapes have a third area as well, and you could expand this question to calculating f13, 31, 23, all of that. But you could do that yourself, but for now, for the case of just introducing how these calculations are done, I'm only going to do f12 and f21 for these areas. The first case is a sphere of diameter d inside a cubical box of length L that is equal to d. The second one is one side of a diagonal partition with a long square duct. So this is basically looking more like this. It's a duct. Whereas this one is actually contained like a box. This is more like a sphere inside that box. And then the third one is end and side of a circular tube of equal length and diameter. So in order to calculate f12 and 21 for the first shape, which was a sphere inside a box, I write the simplest relation that I know so far. f11 plus f12 is equal to 1. The fraction of radiation arriving at 1 plus the fraction of radiation arriving at 2 is all that there is to it. That would become all my radiation. That's why it's equal to 1, the fractions. Surface 1 is a sphere. It's a convex surface. We know that that type of surface does not have any radiation coming off of it that is intercepted by itself. So f11 I'm going to call 0. And as a result, f12 is going to be equal to 1. Now, I need to calculate f21. There's another rule that I know which says A1 f12 is equal to A2 f21. And I know that I have f12 in all the areas, so I should be able to get f21 from here. A1 is my area of a sphere, which is 4 pi r squared or pi d squared. So that's pi d squared. f12, I'm just going to write 1, or yes, let's call it 1 just in this step. I already calculated that this f12 as 1. And then area 2 is going to be the area of a box, which is going to be how many sides is there to a box. There's 6 sides to the box. The areas of those 6 sides is going to be, well, 6 sides, and each one of them has area d squared, f21. So I'm going to cancel the d's, and I'm going to arrive at f21 at pi over 6. This is my pi over 6 for f21, and I already have f12 here as well. Now I move on to the second shape. In the second shape, again, I want to calculate f12 and 21. This is area 1, and 2 is the one on the right-hand side. So again, I'll start with my easy relation, f11 plus f21, 12 plus f13, is equal to 1. So now, again, I look at my area 1. It's a flat plate or flat surface, so if f11 should be equal to 0 for this case. And then now I'm left with f12 and f13, which are equal to 0. I also know that there's some symmetry. 2 and 3 are facing 1 exactly the same way. So I can say based on symmetry is with 2 m's. You know what, I'll just say based on symmetry, I'll have f12 plus, well, equal to f13. Because they look exactly the same when we're looking at them from 1. So f12 and f13, or the portion of radiation going from 1 to 2 is equal to that portion going from 1 to 3, which makes us arrive at the conclusion that if f11 is equal to 0 in the above relation, plus f12, for f13 I'm going to rewrite f12 again because it's equal to f13, and then I'm going to arrive at 1. So as a result, f12 is equal to 0.5. Now again, I need to calculate F21 as well. So F12 multiplied by area 1 is equal to F21 multiplied by area 2. And I have F12 as 0.5, so that one I'll just leave here. How about area 1? Area 1 is the diagonal length, which I don't have. I have to calculate, and I know that this is more of a duct shape, and I don't have the length of this. Whenever you don't have the length, make an assumption, like pick a parameter and call that the length. It should cancel probably later, and if it doesn't, then you'll just suggest the relation based on the length that you assumed. So I'm just going to call that length L prime, and the diagonal length for A1, I'm going to use Pythagorean theorem, and I'm going to say that it's equal to L square root of 2. You can actually try it, but it becomes L square root of 2. So L square root of 2 multiplied by L prime becomes the area, this area A1, basically. So L square root of 2 L prime, that's area 1, and then I go to F21, which I need to calculate, so I leave it as that. And then A2 is going to be the length of A by the length of the duct itself, LL prime. That will be this area. L prime is this length, and this side of it will be L. So LL prime, as I was hoping, my L prime is getting cancelled. L also gets cancelled. So then I'll have F21 equal to square root of 2 by 0.5, which is square root of 2 divided by 2. This is my F21, and my F12 I already calculated as 0.5. So for calculating F12 and 21 for the third shape, I need to go to the tables available for me. This is a little bit more complicated shape. So for this one, again, I'll start with my relation that says F11 plus F12 plus F13 is equal to 1. And then I know that F11 is equal to 0 because surface 1 is looking flat, so it doesn't really radiate on its own. So then I'll have F12 plus F13 equal to 1, which doesn't quite help unless I have F13. In order to calculate F13, which is radiation from here to here, I'll go to the table for the three-dimensional different view factors for three-dimensional shapes, and then I'll have this shape that can help me. I have two circles, which is what I call coaxial parallel discs. So this is exactly looking like my shape. All I need to know is this L over Ri and Rj over L in order to be able to use the figure and actually calculate my Fij. This, if you were in the book, you would be able to read it as Fij. So let's now write L over Ri. L over Ri is going to be equal to, the length is actually equal to my diameter. So it's d, and my Ri is d over 2, which gives me 2 here, which is, I'm here. And then for Rj over L, I'll have again d over 2 divided by d, which gives me 0.5, which means that I'm in this curve, a curve in the middle of the 0.4 and 0.6. This is 0.4 and this is 0.6. This is becoming a little bit more complicated, but I'm actually going to pick 0.4 here, 0.6 here, and I'm going to pick this point here. So based on that point, I should arrive at around Fij, that is around here, just before 0.2, and I'm going to say that my Fij in this figure is going to be 0.17. Now for my case, Fij is my 3 to 1, so I'm going to arrive as F3 to 1 as 0.17. And based on symmetry, 3 to 1 or 1 to 3 is exactly the same, or in other words, the areas are also the same. So F3 to 1 is equal to 0.17, which is going to be equal to F1 to 3 as well. They're having the exact same area. This is all symmetrical, so I can arrive at that. So now that I have F13 equal to 0.17, I can now go back to my relation 1 and say that F12 plus 0.17 is equal to 1, which gives me F12 as 0.83. Now that I have F12, which is one of the things I wanted to calculate, I now have to calculate F21, which again, I go back to the relation that I typically use. I say A1 F12 is equal to F2 F2 A2 F21. For my A1, I'll have my area on the circle on the top. That's going to be pi d squared over 4. F12 is going to be 0.83. Oh, whoops. 0.83. A2, area 2 is the area surrounding this cylinder, which is pi d is your perimeter multiplied by the length of it, which is another d. So pi d, the perimeter, multiplied by the length, is another d. That would be my area 2, F21. I have to cancel this d squared with these two d's, and the pi gets cancelled as well. What I'll arrive at will be F21 is 0.83 divided by 4, which becomes 0.21. This is the other view factor that I was looking for.